All right, hello. This video, I'm going to be going through and discussing the many different energy types that I went over in physical science. This is meant to be a review. Some of this we have already lectured over, but I felt that some people may have had a little trouble focusing because the lecture was somewhat disjointed because some of you were, let's go with amusing that day. So I'm going to go ahead and go back through everything that we've already talked about, as well as cover the other half of the information that we had not gotten to yet. So I will periodically, from time to time, step off screen and give you an opportunity to pause the video so that you can write down any information you need to. I'm going to have a map on the board. It's meant to be kind of an outline. I am not writing down everything because this is a video, and you can back it up and listen to it again if you miss something. So, with that said, let's get started. Now, the first thing that I want to mention is the law of conservation of energy. Okay, the law of conservation of energy states that energy can never be created or destroyed. It can only be transferred from one form to another. These 6 represent the 6 forms of energy that we're going to be talking about, or the 6 forms that we can see energy as. There are more or less, depending on who you talk to. Technically, electrical can be considered to be part of electromagnetic, and there is also an argument to be made that magnetic energy is a thing. Nuclear and chemical could arguably be combined, depending on how you're looking at it. So this is not the all-inclusive only way that you can see this information. But it is the way that I am going to teach it in this class, and it's the way that I'm going to be quizzing you over. I'm going to be going through each of these one at a time after kind of going through some of the core information on each. Some of them we're going to be talking about more than others, because some of them you need more information about, where some of them you've already talked about quite a bit in previous classes. We're going to save mechanical for last because that's what the physics class is actually going to be focused on the most. So I'm going to go through the rest to give you some information on them, and then we can start mechanical and just kind of keep going from there. And this may or may not be the same order that I went through them when we first talked about them. I don't remember, but we're going to start with thermal energy. So thermal energy is energy of heat. It's what temperature is meant to measure. It's measuring the amount of thermal energy in a couple of different ways. It's not the absolute measurement, but that's the purpose of temperature, is to track thermal energy. Thermal energy is often considered a waste energy. Most of the time, a lot of these energy types, due to different interactions, will end in thermal energy. It's energy that is lost in systems will actually be transferred into thermal energy rather than actually being lost, because energy, as we already said, can't be lost. It just changes from one kind to another, moving back and forth, but pretty much all energy dies here. This is where it ends up. So thermal energy is energy of heat. It's the waste energy. It's the byproduct of most processes that happen all over the world and even inside of your own body. Thermal energy is the waste. From there, let's talk about chemical energy. Now, chemical energy is energy that has been stored within chemical bonds. Okay, if you think about what an atom actually is, okay, an atom is a group of subatomic particles that are held together by things that we're not going to get into right now. Protons and neutrons in the middle, and then electrons flying all around the outside. Well, when bonds form between different atoms, those electrons are forming that bond. It takes energy input to make that bond happen, to link those two atoms together to the point where they'll be linked. They can't get away from each other. That is energy that is being physically put into a location to prevent something else from happening. So the penultimate example of this in your body, or in all animals, is ADP versus ATP. adenosine diphosphate and adenosine triphosphate. Adenosine diphosphate has two phosphates, that's what di means, has two phosphate ions that are attached to the side of what we call adenosine. As your body breaks down food, as it goes through the processes that you talked about in biology, that energy is captured and used to attach a third phosphate ion onto the end of the two phosphates that are already there, turning adenosine diphosphate into adenosine triphosphate. And there's a small amount of energy that's stored in that bond every time it's formed. And so your body creates ATP molecules and then sends those ATP molecules away to provide energy to other places. Basically, ATP is a charged battery and ADP is a discharged battery. Your body takes the energy from your food, uses it to charge an ADP battery, turning it into ATP, sends that ATP off somewhere else, so where it will be discharged, turned back into ADP and releasing the energy that was stored, and then that ADP will come back to the mitochondria where that third phosphate will be reattached to recharge that battery. But ultimately, chemical energy is just energy that's stored in those bonds. And that is one specific type of bond, but every bond has chemical energy in it. Every one of them. Water molecules have energy in them. The molecules in sugar have energy in them. That one's a little more obvious, I think. But the chair that you're sitting in, or the couch that you're sitting on, or if you're lazy and still in bed, that bed is made literally of chemical energy. The atoms that make up the molecules that make up the materials that bed is made of are chemically bonded together, and so they hold chemical energy. And then within those atoms, we not only have the bonds that are linking different atoms together, but we also have that nucleus, and that's where nuclear energy is found. Nuclear energy is the energy contained within the nucleus of the atom. Now, that energy is vastly superior in quantity than anything you'll find in chemical energy. Nuclear energy is much harder to harness, but much, much more powerful. There's a lot more of it. And so when we manage to release it, well, we get things like bombs. It's very easy to accidentally create a nuclear bomb in the process of trying to harness that nuclear energy. And ultimately, a nuclear reactor is using the exact same process that detonates a nuclear bomb. We've just got more means in place to control that reaction, to slow the reaction, so that rather than all of that energy, nuclear energy being released at once, it's released more slowly. It's controlled with things called control rods, which we'll talk about a little later. Now, nuclear energy at its core, it's just energy in nuclear bombs. But there are two ways, as I said, of harnessing that energy. So I'm going to move this over for a sec. So those two types of nuclear are going to be fission and fusion. Now, fission means breaking down, while fusion means putting together. So, in a fission reaction, a nucleus is broken. You take a large nucleus, you hit it with a neutron, and it splits into two smaller nuclei. That's the plural of nucleus, is nuclei. And from that, more neutrons are released. Each of those neutrons then goes off and hits another nucleus, causing it to split off, releasing more neutrons. And it's what we call an exponential or logarithmic reaction. The more nuclei that break down, the more neutrons are released, and the more nuclei there are that can be broken down. And so the rate of reaction increases very, very, very quickly until all of this energy is being released in a very short period of time. Well, that's a bomb. When all that energy is released over a short time, that's when we get a bomb. In a nuclear reactor, we have these things called control rods, and what they do is they absorb neutrons. That's it. That's all they do. When neutrons are moving through the area where the nuclear material is, some of those neutrons, or maybe most of those neutrons, are absorbed by the control rods, limiting how fast this decay can happen. So there's only a limited number of neutrons available to smash into nuclei and break them apart, releasing energy. And that's how we control that reactions with those control rods. But all they really do is absorb the neutrons to prevent the destruction or the fission of too many nuclei from happening at the same time. Now, fusion is when we go the opposite direction. Rather than destroying or breaking a nucleus into smaller pieces, we're combining them and making larger nuclei out of smaller ones. For example, and I may be misremembering the exact numbers here, so bear with me. But if you take, I believe it is 6 deuterium nuclei. Deuterium is an isotope of hydrogen. Okay, it's hydrogen 2. That means there's 1 proton and 1 neutron. If you take 6 deuterium nuclei and smash them together in just the right circumstances, you will produce 1 helium-4 nuclei. Okay, and so that process is called fusion. And in that process, way more energy is released than here. And that is because the protons and neutrons from that third hydrogen atom, that third deuterium atom, they kind of disappear. They are transferred from completely back into energy. All of the stored energy there is completely released, and it's turned back into pure, unmitigated thermal energy. Which, by the way, is the way most energy, when fission takes place, it's thermal energy that's released. But in fusion, we're taking 2 subatomic particles and basically annihilating them, releasing them purely into energy, and that energy we can capture as thermal energy and use it to do the same thing that we're using the thermal energy from the fission. But it takes much less of it to make it happen. Now, the problem with this is that even the theoretical version of this, which we have never actually managed to accomplish in a controlled manner on Earth's surface, cold fusion takes place at about 100 million Kelvin. Normal fusion, the fusion that happens in stars, takes place at more like 400 million Kelvin. So this is not something we've actually managed to use in anything other than a bomb. We've never managed to do this in any kind of controlled environment. This we can do in a controlled environment pretty easily these days. This is still a bit of an obstacle. Okay, once my coughing fit was over, I went ahead and put a little more information on the board here. Okay, so the next one we're going to talk about is electromagnetic energy. Now, electromagnetic energy is light. That's what electromagnetic energy is. It is energy in the form of light. Okay, so there are multiple spectra of light. Another term you may have heard, it's associated with some of these. These are all also called radiation. Okay, so this is electromagnetic energy, electromagnetic radiation, electromagnetic spectra. It all refers to the same thing. So we're going to start here at the top of this list. We'll move down a little bit, and then we'll see where we go from there. I'm not 100% sure yet. So let's start with radio waves. Now, radio waves are the lowest energy form of electromagnetic radiation. Okay, they have a very, I'm going to put this up here. They have a very low energy, a very high frequency, and a very low wavelength. Okay, and as you move down this list, these tend to go the opposite way. So as you move down, energy increases, meaning this stuff down here is very high energy. But the I can't point. There we go. Frequency will frequency will go down. That's wrong. I'm sorry. Hang on. Those are backwards. These are low frequency and long wavelength. So as you go down this list, the wavelength will get shorter, and the energy and frequency will get longer or higher. So radio waves are what our radios use. XM, I think, uses something else, but AM and FM radio use radio waves. Radio waves can be a couple of miles long. They have a very, very long wavelength, which isn't something you guys have to worry about too much right now. Microwaves are a spectrum of light. And some of you are probably seeing the word microwaves and thinking, now, don't I have a thing in my house that is called something similar to that? And the answer is yes. And that does, in fact, use microwaves to cook your food. The irony is, microwaves are also very low energy. Red light has more energy than a microwave does. But yet, microwaves can cook your food in not too terribly long. So you might be wondering, why is that? What allows that to happen? Well, microwaves, the microwaves that you purchase at the store, resonate with a particular molecule, specifically the water molecule. There is a specific wavelength of microwaves, or a specific range of microwaves, that will actually cause a water molecule to oscillate. So if you imagine the two bonds that connect the hydrogens to the oxygen as springs, it will cause those springs to start bouncing and exciting more and more and more. And they'll start, like if these are the hydrogens, then it will start them moving in and out some, but it will also start them oscillating and swinging around. It increases the energy within the water molecule itself. That's why if you want to cook something in the microwave, you have to add water to it. What it's actually doing is heating the water, because it causes that resonance within the water molecule itself. That resonance allows that electromagnetic energy, the microwave, to be converted into thermal energy specifically within the water. But because the water is then in contact with your food, that thermal energy then flows from the water into your food, cooking your food. Anything that has water in it can be cooked in a microwave. So yeah, and that's why if you try to cook something that you're supposed to cook with water, without water, it will burn, because everything has some amount of water in it. Like if you try to cook pasta without putting water in it, it'll burn. You'll see black start to appear in it, because the water that's inside of the pasta is heating up, gaining an incredible amount of energy, but it can't do anything because there's not enough of it. And so it just burns the sugars that are around it rather than actually cooking everything. Then we have infrared. Infrared is a light that I'm not going to spend too much time on. Infrared is the light that body heat. Your body radiates infrared light. The Earth itself radiates infrared light. Infrared is one of the things that we use looking out into space to try to detect other galaxies and stars, in addition to visible. We can actually pick them up pretty easily with infrared. And then right here, smack dab in the middle, we have visible light. Now, visible light is the only type of light on this list that we can actually pick up with our eyes. In fact, our eyes are keyed towards picking up yellow light specifically. And then as you move away from yellow, yellow-green, as you move away from those, your eyes become less and less effective at distinguishing between colors. That's why oranges, reds, purples, and blues are more likely to be mixed up, because your eyes aren't quite as good at distinguishing them as yellows and greens. And there are, of course, 7 colors of light according to physics, and then white light versus black light. I'm not going to get into that in this video. Then we have ultraviolet. This is the stuff that gives you sunburn. Our ozone layer specifically filters out ultraviolet or UV light. As that UV light gets through, I don't remember whether it's A and B or B and C, but the ozone, I think it's A and B. The ozone layer is particularly good at filtering out UVA and UVC, UVA and UVB, apologies. But UVC, it's not so good at, and so that's what usually causes sunburn. UVA and B are far more dangerous and can actually do damage to your skin in seconds rather than the minutes or hours that it can take for UVC. Now, it's possible, I have my letters backwards there, it may actually be A is the one that gets through and B and C are the ones that filters, but it doesn't matter for this purpose, for this discussion. X-rays. X-rays are even higher energy. So if UV gives you sunburn, why do we use X-rays for skin or for getting pictures of what's happening in your body? Well, you are exposed to a very, very small amount of X-rays when you get an X-ray. And yes, that's why it's called an X-ray, because you're actually being exposed to X-rays. And X-rays are high enough energy that they literally pass through every form of soft tissue in your body except bone, because bone isn't soft tissue. And so it's really, really good for X-rays, allow us to get really good images of bones without having to cut you open and take a look at it. And then we have gamma rays. So this symbol here, that's a rough approximation of what a gamma is supposed to look like. Gamma spelled G-A-M-M-A. Gamma rays are the most dangerous form of radiation. When we talk about radiation from nuclear bombs and nuclear weapons, we're usually talking about gamma rays and sometimes X-rays, but this is the stuff that kills you. X-rays can also kill you. UV can kill you in high enough amounts, but the dosage that we usually see is very small. Gamma rays are not something you're generally exposed to in very high quantities. I'm not going to give numbers because I'll be misquoted on it probably, but yeah. So these are our forms of electromagnetic energy. These are the 7 spectra of electromagnetic energy. Okay, now we're going to move on to electrical, which will leave us with mechanical as our last one once we've gone through this. Now, electrical energy is a little weird. So, electrical energy and electricity are related, but not exactly the same. Okay, so there are 4 terms you need to know when we talk about electrical energy or electricity, because like I said, they're related. Those are voltage, current, resistance, and power. Now, voltage is a couple of things. For this class, what we're going to say is voltage is how we measure energy in electrical systems. This is not exactly the same thing as energy. Okay, it doesn't mean energy, but for the layman, this is basically energy. This is how much energy a circuit requires or is capable of outputting. Now, it's actually called the potential difference, or the difference in the potential. And that will become, the reason why that's important will become clearer later. Current is a measure of the flow of electrons through whatever. Hopefully through an electrical circuit, but potentially through you if you do something stupid near an electrical circuit. Current is what kills you. Okay, this is the thing that when you hear about people dying from being electrocuted, this is what kills them. You can be hit with millions of volts, and you'll be sore, but you're probably going to survive. Current is another issue. Current will kill you very easily. I believe it is 7 milliamps going across your heart. That is 7 thousandths of 1 amp is all that it takes to kill you. Power is the amount of energy that is expended over a certain period of time, and resistance is a measurement of how hard it is for electrons to move through a wire or other element. There are other words and other terms besides resistance. Resistance is the only one I'm going to cover today. So, voltage is basically how we measure electrical energy. Current is a measurement of how many electrons are moving through an area. Power is how much energy is being used in a given amount of time. This could be compared to like velocity. So like distance. Distance is how far you go. Time is how long it took. Velocity is how fast you were going. Well, if energy is how far you went, it'd be kind of like the distance. Time is still how long it took, because time is still time. Power is how much energy you used in a given amount of time. So this would be kind of akin to velocity from kinematics. And then resistance is just how hard it is for stuff to move through a circuit. So electrons are moving through or across a wire. That's what causes electricity to work. But the resistance within that wire can affect how efficient that wire might be able to function. And that's all I'm really going to cover for the electrical end of things today, because this video is almost a half an hour long already. So I'm going to pause it, and we'll move on to mechanical. Okay, so from here, we're going to start talking about mechanical energy. And there are 4 primary kinds of mechanical energy. Those 4 are translational energy, gravitational energy, rotational energy, and elastic energy. Now, 3 of these you have read about already, though this one wasn't called translational in this chapter. We'll get to that later. Rotational is not in this unit. I am mentioning it because I want you to understand why it is present in the equations that you're going to see, but we're not going to use this at all in this unit. In the next unit, where we start talking about rotational mechanics, rotational will be something we talk about quite a bit, obviously. So first off, I want to go through what each of these are. Some of them are pretty self-explanatory, but translational energy is the energy of something that is translated. Now, translating in, if you've paid attention in math, you should know that translating means moving from one location to another. That's translation. Generally, when we talk about translation, we're talking about linear motion. Something traveling in a straight line from one location to another. But traveling across a curve is also considered translating. So, for example, when you drive from one location to another, that is translating. The Earth, in its trip around the sun, it is traveling in a circle, but it is still considered to be translating because it's traveling in a roughly linear path. Now, the reason why, again, when we get to rotational systems, we'll talk about why traveling in a circle is considered the same thing as traveling in a line. Like I said, we'll get into that. Gravitational energy is energy that comes from elevation. So this is energy that is created specifically from exposure to a gravitational field. So anything that can be said to be at height is going to have gravitational energy. So for example, grab a marker. This marker has gravitational energy because I have elevated it up off of the floor. If I drop it, that gravitational energy will be converted into translational energy as it travels in as straight a path as it can back down to the floor. So gravitational energy is a little easier to spot. Now, I also, at this time, have gravitational energy. But even if I laid down on the floor, I would still have gravitational energy. Because I am separated from the center of the Earth by some amount of distance. And that is where my body is trying to get to, is towards the center of the Earth. So I have gravitational energy even where I am right now. Okay, even though I'm not moving or falling or really elevated technically, I am elevated above the center of the Earth. And the Earth is trying to pull me towards its center. So I still have gravitational energy. So when we start talking about gravitational energy, we are really talking about relative gravitational energy. Okay, because you can, if you climb higher and higher, your gravitational energy is going to increase. But you can go lower and lower as well, and your gravitational energy is going to decrease. So the tip that I always tell everybody is the bottom of the problem is h equals 0. Whatever the lowest point in the problem is, that is where height should be considered to be 0. Because you can make height anywhere technically from the center of the Earth. Anywhere between here and there could be called the bottom. The bottom is relative because everything's trying to get to the center of the Earth, but it can't get there because the Earth is in the way. So call the bottom of whatever problem you're working h equals 0. Rotational energy is the energy of something that is spinning, like a top. Okay, traveling in a circle is not spinning. Spinning is when something is spinning. Revolving and rotating are not the same thing. Revolving is a type of translation. The Earth revolves around the sun. It travels in a circle around the sun. But rotation means spinning, like I said, like a top. If you spin the top while it's sitting there and spinning around, it has rotational energy. And if it's moving, walking around the table, then it also has translational energy because it's translating from one location to another while spinning. And then elastic, the other one that is in the textbook, elastic energy is getting into energy that is the result of stretching or compressing. So if you think of a spring, if you stretch a spring out, you can feel it trying to pull your hands back together. That is a form of energy. You have put energy into it by trying to stretch it out. If you do the same thing in the other way and try to compress a spring, you can feel it pushing your hands out. So there's energy there either way. So yeah, moving, elevation, spinning, and stretching or compressing. I'm going to pause this now and then zoom out and talk about the two types of energy, and then we'll wrap up there. All right, so the last thing I want to talk about is kinetic energy versus potential energy. Okay, kinetic energy is energy of motion. Potential energy is energy that has been stored in one form or another. Now, I'm going to go through all 6 of these and talk about what they are. Some of them can be both. Some of them are only one or the other. Okay, so we're going to go in the same order we did when we first went through them. So we're going to start with thermal. So thermal, it's the energy of heat. Well, heat is movement. At the end of the day, there's no other real good way to describe it. It's bonds vibrating or swinging around. That's what causes thermal energy. That's how we measure thermal energy, is vibrational energy within molecules. So thermal energy is a kinetic energy. Then over here, we have chemical energy and nuclear energy. Now, chemical energy, if you look back, I'll tell you that it was energy that was stored in the form of a chemical bond. So chemical energy obviously is stored energy. Nuclear energy, likewise, is energy that is stored within the nucleus of an atom. So it is a potential energy. They say this is potential, this is also potential. I feel like I said kinetic, but I'm not re-recording this video if I did. I apologize if I did. This is potential. Okay, then we have electromagnetic. Now, electromagnetic energy is light, and light is always constantly moving. So electromagnetic energy is kinetic as well. And then the last two, electrical and mechanical, both can be both. Electrical energy can be perceived as kinetic energy or potential energy. Think about a battery. A battery has electrical energy stored within it. And when you hook that battery up to a circuit, you can make things happen, like turning on a light bulb. Well, a light bulb can only light up if electrons in the current are moving through the circuit. So electrical energy can be stored in the form of a battery, that's potential energy, or it can be kinetic when it's actually generating electromagnetic and thermal energy in the form of a light bulb. We can actually turn electrical energy into electromagnetic energy and into thermal energy. Just touch a light bulb sometime. Don't do that. But it'll exemplify that. Light bulbs heat up very quickly. So electrical energy can be both. And then mechanical, in these four types, which we're going to be talking about extensively over the course of this unit, translational energy is actually called translational kinetic energy. And I may have said that one or two times in the video, but this is translational kinetic because it is literally movement. It's moving, therefore it is kinetic. Gravitational is gravitational potential energy because as I lift the marker, I am storing ever more work within it. Storing ever more energy in it. And the higher it is, the more energy is stored. When I let it go, all of the energy that's contained within it will be released and it will fall. And the higher I drop it from, the faster it's going to go. If we ignore air resistance. Which we do, because this is basic physics and we're not going to get into the hard stuff. Then we have rotational. Rotational, we said, is the energy resultant of spinning. So spinning is moving. So obviously, this is also another form of kinetic, rotational kinetic energy. And then the last one, elastic, which actually in the text is referred to as spring energy. I meant to mention that, I forgot to. So elastic potential energy is also another stored energy. When you're compressing a spring, you are storing energy within that spring. When you stretch a spring, you're also storing energy within that spring. If you don't believe me, take a rubber band, cut it, and then pull it away and let it go and let it hit your hand. You'll feel all the energy that was stored in there. All of that was from stretching it. Now, you can't compress a rubber band, but you can. Any spring that you tried this with would probably break your arm, so don't try it with a spring. That is it for this. I'm kind of off the way now. That's where I'm going to end this video. I hope this helped give you a little bit of an introduction. I know it was a bit of a mess because I haven't done this in a couple of years, but oh well. Hopefully I will see you guys back in class on Thursday. We'll see.